What's up, everyone? This is a video for section 6.2, and in this video we're going to be looking at some various angle applications, all right? How to find arc length and area of a sector, as well as calculating linear and angular speed for an object that's in circular motion, okay? So let's start with arc length, all right? We know that if we take an angle and we think of it as a central angle that is subtending the edge of a circle, that creates an arc, right? The length of that arc we're going to designate with the letter S, okay? So in general, for a circle of radius r with a central angle of theta radians subtending an arc whose length is S, we can find that length with the formula S equals r times theta, where theta has to be an angle measured in radians. And here's the reason for that. Recall that the number of theta radians is equal to how many times the radius is being wrapped around the circle. Okay, so if we have an angle of 1 radian, that means you're taking the radius of the circle, you're wrapping it around um, one time around the edge to create the arc. Okay, so then the length of that arc is simply just found by treating theta in radians as a scale factor on r, right? You just take your radius, you multiply it by how many times it's being wrapped around the edge of the circle to create that arc. That gives you your length, okay? So let's find the radius of a circle, which has a central angle of 45 degrees that subtends an arc of length 8 inches. And we'll round our answer to 3 decimals, okay? So look at your givens. You're given an angle of 45 degrees. Now I'm going to need to think of that in radians. 45 degrees is equivalent to pi over 4, okay? You are also given the length of the arc, 8 inches, so that's an S value. All right, so if I want to find my radius here, utilizing the formula S equals r theta, S is 8, theta pi over 4. So of course, to solve for r, I'm going to divide both sides by pi over 4, or multiply by its reciprocal, and that should lead me to r equaling approximately 10.186. And this is a length, so the units here should be inches in this example. Okay. All right, now let's transition to a sector. A sector is the region of a circle bounded by a central angle and the intercepted arc. Think of a sector, it's like a slice of pizza. So that's the blue region on your screen here. Okay, and of course the sector has an area associated with it. You can find that area by taking the area of the entire circle and multiplying it by the fraction of the circle that's created by the angle of the sector, okay? Well, we know that the area of an entire circle can be found with the formula pi r squared, right? And then the fraction of the circle created by theta can be found by theta divided by 2 pi, okay? Well, why 2 pi? Because there's 2 pi radians in one complete circle, okay? Now notice, to utilize this formula, my angle has to be in terms of radians as well. So let's simplify this. Let's say we have pi r squared being multiplied by theta over 2 pi. Think of that pi r squared as over 1. And notice I can reduce away pi here. And that leaves me with r squared times theta over 2. And it's common that we write this as 1/2 times r squared times theta. Okay? So let's say a sector of a circle has a radius of 5 centimeters and a central angle of 3 radians. Let's find both the arc length of the sector as well as the area of that sector. Okay, so think about your givens here. Given an r value and you're given a theta value. And the nice thing about theta here is it's already in radians, okay? So let's find arc length. So utilizing S equals R times theta. R is 5 centimeters, theta is 3 radians. 5 times 3 is, of course, 15. And this is a length, so the units in this case need to be centimeters. Okay. What about the area of this sector? Well, utilizing the formula from above, area is going to equal 1/2 times 5 squared times 3. That'll lead me to 75 over 2, or 37.5 square centimeters. Okay. Now let's transition to the concept of circular motion. Suppose an object moves around a circle of radius r at a constant speed. That object is said to be in circular motion. Okay. As the object moves around the circle, it has a distance that it travels. That distance can be thought of as an arc length, s. Okay. Now, if you take the distance traveled, s, and consider it in the amount of time that it takes to travel around that circle, that's considered the linear speed of the object. And we're going to use the letter v to represent linear speed. So v is found by taking the distance that you've traveled over the amount of time it takes for you to travel that distance. Okay, so v equals s over t. Linear speed is not a new concept to you. When you're riding or driving in a car, there is a linear speed associated with the car at any given moment. 60 miles per hour, for example, is a linear speed. It's a measure of distance over time. Saying I'm traveling 60 miles per hour means if I keep that constant speed, in 1 hour's time, I'm going to travel 60 miles. Okay. Now, this object also has an angular speed associated with it, which we're going to represent with the Greek letter omega. Omega is just kind of looks like a W. And the angular speed is going to be the angle theta in radians that's swept out divided by the elapsed time that it takes to create that angle. So that means that angular speed omega can be found by taking our angle, dividing it by the time it takes to create that angle. Revolutions per minute is an example of angular speed. Okay. So when you're driving in the car, not only is there a linear speed associated with the car itself, but there's an angular speed with the tires. Okay. There's a certain number of revolutions that the tires are covering in a given amount of time. Okay. Now, if we take the two formulas for linear speed and angular speed, we can relate the two speeds to one another. Okay, so starting with linear speed, we just said that that was equal to s over t, and s we can think of as an arc length. Now we know that s is defined to be r times theta, right? So r times theta over t, that can be thought of as r times just theta over t, and we just defined theta over t to be omega. So that means linear speed is equal to the radius of the circle that the object's traveling around times the angular speed of the object. Okay. Now, in order to utilize this formula, notice that your angular speed, it has to be measured in radians per unit of time. All right, so let's apply these concepts to this final example. We have a child spinning a rock at the end of a 2-foot rope at the rate of 180 revolutions per minute. This rock can be said to be in circular motion. Okay, you can think of the length of the rope as the radius of the circle that this object is traveling around, okay? So this 2 feet is an R value. And then if it's traveling at a rate of 180 revolutions per minute, that is an angular speed, okay? Now notice what we're being asked to find here. It says find the linear speed of the rock. Well, linear speed, we have two formulas we could utilize. We first define linear speed to be S over T, but then we also define it to be R times omega. So based on my givens, I'm going to use the second formula here. But there's one catch. I can't use it right away because my angular speed is in terms of revolutions per minute. I need it to be in terms of radians per minute first, okay? So I'm going to take omega, which is, again, initially given as 180 revolutions per minute, and I'm going to multiply this by a conversion fraction. I know that there's 2 pi radians in every 1 revolution, right? This allows the revolutions to wipe out. You're left with 360 pi radians per minute. And now we are able to utilize our formula for linear speed of V equals R times omega. So R is 2 feet, omega is 360 pi radians per minute. Multiplying together, you get 720 pi. Doesn't mean a whole lot to me in that exact form, so I'll approximate it. 720 times pi is approximately 2,261.9, and this is a linear speed, so the units should be a length, a unit of length divided by time. So in this case, feet per minute. Okay. Look how that's traveling pretty far in 1 minute's time.